Ready to go? So, okay, so the goal today is to understand the execution model of the kernel, just roughly speaking, understand how the things are running by one time. Talk about how we can initialize other CPUs and start talking about scheduling. So let me start again on this. So just check. Okay, yeah, this is the camera. Let me. So this is our microkernel, right? This is what we were. This is what we were building. So far we mostly talked about this very first CPU 0, right? But obviously our goal is to support multiple physical CPUs, right? So typically Intel calls the CPU a bootstrap processor, and those guys are application processors. The protocol which Intel plays is that they do get run for a little bit to initialize the caches and everything, but mostly it's controlled by the BIOS. But essentially, when the bootloader starts executing, only this bootstrap CPU is executing, and all of these are sitting idle, waiting for a special interprocessor interrupt, right? So, and what we were discussing up until now is that remember we started from the bootloader, which we just dropped, and then this bootloader started executing the main function of the microkernel. This main function of the microkernel initialized the memory manager, which keeps track of all available physical memory. We also created the kernel address space, which maps this physical memory one-to-one, and also actually it doesn't allocate anything for the user because we don't need anything for the user. But what we also said, okay, we will create process 0, which has the following layout of the other space. So it also starts from address 0, maps all available physical memory one-to-one. So this is this one-to-one mapping to these two address spaces. These two are virtual, and this is a physical address space, right? And also at some max address, which we have to pick while doing the homework, we essentially said this is the user part of the address space. This will be privilege level 3, all of it as privilege level 0, right? And essentially, we loaded the ELF file of this process. In fact, we said, okay, maybe we're not going to allocate the stack, but we'll be waiting for the memory allocation system call. But essentially, we did this initialization, right, on this CPU 0. We also initialized interrupt, so we have IDT, EDT, and things like that, right, PSS. So we have process 0, and imagine, like, and we will discuss today how the system sees this process 0. But imagine we have some kind of a queue of available processes, and right now it contains only this one process 0, right? So we will call it scheduling queue. Right? And at this point, we are kind of ready to go. Like, we're still running inside the main function of the microkernel, but we want to wake up the application processors to make sure that the system can use all available physical memory, all available resources, like computational resources of the system, right? What do you think needs to happen? So how do we, I mean, two things. How do we actually wake up those CPUs, but also how do we initialize them? What bits of initialization need to be done on those CPUs?
You mean like in the very beginning, when you start the kernel the first time?
Well, like follow my story. So I'm saying we're running in main, like roughly in the order of how we did it in the lecture. Initialize this interrupt, initialize memory allocator. We're able to create the kernel address space. That's kind of important. So kernel address space created the very first process. And I'm ready to go, but want to initialize other CPUs. Just because, okay, we did like on this one, like CR3 on this points to this address space, right? This is the kernel address space. This process 0, if this is the address space of this process 0, then it points, let me just like make up an arrow like
thought
this.
is like, I'm thinking on a higher level, but there might be mirrors here. Usually there's like a manager of multiple threads. I'm thinking some sort of manager where each core is like running a specific loop of some sort or something like that.
You mean some kind of a scheduling loop, right?
Yeah, exactly.
Okay, I agree with this. We need to start running this loop. And we should agree on what goes into this loop, right? That makes sense. And this is what x6 is doing, but give me more details. Oh, yeah.
So our main thread's got an IDT, GDT, TSS. Which of those do all the other threads need? Is it just the GDT and they share the others? I'm not actually sure which do.
I agree with you. Let's figure it out. Because like it's a very practical problem. If I say like make sure it's running, because when you start programming this thing, you have to make a decision. So how to set it up. So let's make an illustration for this BSP. So just to be more concrete, so the R3, it's a hardware register, right? So it points, we said, okay, points to the kernel address space, right? To this one. All right. GDTR register points to the global descriptor table. Inside this global descriptor table, there is a TSS segment, right? Points to the TSS. Inside this TSS, there is a pointer to this stack pointer 0, which points to the kernel stack on which we are ready to receive an interrupt, right? Agree? And we also talked about this interrupt IST stacks, right? They also exist. So let's just, I'll make them small. They're like, what is it? 8 of them or 7, I forgot. 8, it's because 0 doesn't count for whatever reason, I forgot.
Yeah, I think so.
Yeah, I already forgot this. Okay, sure. So this makes sense, right? So this is on the bootstrap processor, right? On the one which we were running. And just to make sure that this thread of execution on which we booted, right? I don't know. Let's call it, let's give it a name. Let's give it a name. We'll call it idle 0, meaning that it's an idle thread on CPU 0. And it also has it has an instruction pointer, like the current state of the CPU. And it has a stack pointer, so it points to a specific thread, right? So we probably need some kind of a thread data structure to make sure that we can at least save, and like when we context switch out from this thread, we can account for this, right? But I'm not sure how to write it correctly. But so like keep it in mind, we'll get to it. But okay, like what about those data structures? So do we need them? What will happen on this? Imagine like application CPU 1. What data structures we need there?
We need to point to different stacks of the kernel to make sure you're handling like concurrent interrupts probably.
Correct, right? So what do we need? Because I mean, obviously interrupts will be enabled. When you disable an interrupt, you disable it only on the CPU, right? You don't disable it globally on the system. Although there might be a way to do it, but it's too slow that no one does it. So okay, sure. So you say we need this stack 0. I agree with you. So if we want the stack 0, which data structures we need to support it?
You mean which could be on each CPU?
Yeah, so if we wanna have this stack here to connect it to hardware, what do we need to do? You need what, all of them? Which,
You need CR3 to point to some unique global descriptor table per
Oh.
core
GDTR,
GDTR.
I agree.
The reason is because like you can't have just one global descriptor table which points to different stacks, like you can't overwrite that value for each core. So you need one copy each of GDT and one copy each of PSS.
Correct. Agree with this. And so this is a nice observation. So GDPR on each CPU will point, well, so this is like, if this is GDTR on CPU 0, this is GDTR on CPU 1, it will point to its own version of GDT. GDT will point to its own version of TSS, right? And TSS will, like, stack pointer 0 will point to this stack, right? Kernel stack. Agree? Makes sense? So we need, like, these data structures, they all become per CPU, right? Right? But this one is actually arguably per thread. Right? Why is that? Because if we context switch away and we said, look, we're executing on this stack when the timer interrupt arrives. So we saved a bunch of information. We saved the context. Right? And so probably this, like, and we will keep it like, we can design it differently. As I said, we can move all of it into some thread data structure, but let's just leave it on the stack for simplicity for now. Right? So probably those stacks are per thread, right? And every time this is important. So every time we will context switch to a thread, we'll touch this stack pointer 0 to point to a different stack, right? So again, just wanted to make sure that, you know, if we have a thread data structure, it will have a pointer to its kernel stack, right? And we probably need some kind of a process data structure. Which will contain a list of threads and will also point to the global descriptor table, which represents as address space, right? Make sense?
Is that, you need a per thread interrupt descriptor table, because the point of the interrupt descriptor table is to point to, you know, kernel handler functions. And because they point to kernel handler functions, they probably are associated with specific instances of the stack, and so they should probably be associated with each thread.
That's a good question. So what's the answer?
It's not like you can like patch because you're not like truly running the threads currently on the CPU. You don't need to have like basically have your
Good, and I agree with your beginning of your answer that you said no, but then I missed, you lost me when was your explanation. So can someone or you maybe reiterate? So what's the reason why? Like per CPU or IDT, is it global? Is it per CPU? Is it per thread?
I think it might work global because it's just associating a function per per vector number. So I suppose there's a little bit extra. There's like it's saying which segments it's associated with. So if you keep your segments in your GDT consistent across all your GDTs, then I think you'd be fine having only one global IDT. But
Correct.
the IDT doesn't track your stack. That's separate. So I think we're fine.
I agree with this. So this is an excellent explanation. So we say, look, if those GDTs follow the same layout, meaning of those segments, since we have a code segment here which has to fetch something from the GDT, like a code segment for the kernel and a data segment for the kernel, it's okay. So if those GDTs are the same, we can just reuse the same data structure. It will be just a number, the same number on all of them, right? And the handler itself, it's an entry point to, handler is a virtual address, so like it will be pointing somewhere here in the kernel virtual address space. And it seems that unless we have a case where we say, look, we want different interrupt handlers and different CPUs, which might be the case in some very exotic setup. So for example, maybe you're running out of interrupt handlers and you want to create something very, very fancy, which I haven't seen in practice, but maybe it does exist. Then you're fine to go with one global GDT. Makes sense? But because like you timer interrupt, you always, no matter which CPU is getting the timer interrupt, you can start executing the handler, right? It's the same address. At least in our setup. So, and maybe there is some exotic setup where you say, look, I want a different address to start executing on a different CPU. I don't know, maybe like you can always, arguably, you can also like always do a dynamic dispatch. So like just inside the handler, you can read the CPU ID and then dispatch and say, look, I will execute one code or another. So it's almost like I don't even see a case where you might be needing it, right?
But what if each CPU has its own virtual address map? Is that ever useful?
I don't see your case, honestly.
Even for privacy?
I never seen a good case. I mean, it again, you might arrive to some super exotic case where you say, look, I mean, I've seen it maybe once in one exotic isolation mechanism where we try to, like you say, hide parts of address space. And then you might have a virtual address space layout. I would say no. Let's just keep it as no, and it will stick like that for like 10 years, and then maybe you will discover a case. So this kernel address space probably is the same on all CPUs, right? Any other question, Manvik?
For the custom handlers in the GPT, would it be under a one-bit lock for any rights in the GPT as global and being accessed by all the threads?
Hold on. We agreed that this.
Sorry, I meant into this specific. Sorry.
Yeah, I did.
Sorry.
Will it be under a lock, especially if you want to update the handler? Agree. Again, it's probably honestly like this, even in practical kernels like Linux, the low-level interrupt entry code is never overwritten. Like it can be patched, but I never seen the case. So typically, the case which people usually have is that you have some virtual table or like a virtual pointer, and you say, look, maybe I'm like implementing some antivirus software and I want to track all available interrupts. And then I first, like, if I have like a real handler timer, I want to first go execute, I want to patch this handler, but it's typically not patched in the IDT, but patched at the next level. Patch is something like antivirus timer to just, I don't know, it just tracks all timer interrupts or just reacts, and then it calls this pointer. Yep. So the question is like how to protect this entry. It can be either entry in the IDT or some other like table like variable, right? And the problem is that the problem is how to ensure atomicity of this access, right? I know the answer, but I don't want to go too far away. So let's think of it, how do we want to?
Could you just do an atomic ray?
Okay, yeah, no, Ali is helping me. Okay, so first of all, let's understand the atomicity concerns in. Imagine this is like a word size pointer, 64-bit, right? On a modern machine. What kind of synchronization issues you might face with this atomic number? Jesus, it actually goes kind of deeper into the woods, but sure, let me talk about it. All memory accesses, or like communication with the caching hierarchy, with the memory subsystem, are performed in the units of cache lines, right? So do you know the size of the cache line on Intel CPU?
Doesn't it depend on your processor?
On Intel, it's actually fixed on all modern CPUs. It's one number. It's useful to remember. Like it's like all caches, all transactions with memory, starting from cache L1, L2, L3, and the memory subsystem.
So
The word. Any other
128 bytes?
128 bytes? But okay, how do you when you guess those numbers, is it a truly guess? You never heard it? Never. Okay, so the number is chosen to kind of like strike a balance between probably hardware overhead to manage smaller numbers, like 8 bytes numbers, and on the other hand, like you saying like I only want to access a subset of this cache line, and you bring the entire cache line throughout the entire caching hierarchy. So sometimes you leverage the spatial locality, meaning that you might access the next couple of bytes in the same cache line, but it's also not always the case. Sometimes it's a truly random access, like in a hash table. So you accessing like those things all over the place, but wasting the bandwidth of the memory subsystem. So Intel chose 64 bytes. If you ask me, like I cannot give you a better answer. So 128 maybe would be an equally good answer, but they chose 64 bytes. Like I don't know exactly what kind of simulations or what kind of analysis they run, but this is their access size. There is an interesting observation about the cache lines. Accesses to the cache lines are always atomic, meaning that, like as Talia says, if this thingy is fully contained within the cache line, then you never will see a torn read or write, meaning that you start writing it, like you do a move into this address, and somehow someone else does a move on the other CPU, and you end up with a cache line which is torn in half, meaning that half of it is written by this move and half of it is written by the move from a different CPU, right? It's called the torn write. Make sense? So because the way the cache coherence works, the protocol which ensures that it introduces some sanity into how you access those cache lines, is the CPU which does the move acquires the cache line, and the cache line stays for the duration of the entire write. If you do another write, there is no guarantee, because another CPU might send a request. If you have 2 moves in a row, then this cache line might be moved to a different CPU, perform this write, and move it back, right? So, which means that, well, maybe like you might see some issues here, but as long as it's within the cache line, the writes are atomic, right? Okay, sure, but how do we ensure that this field is not in between the cache lines? Because the moment we place this 8-byte field, and who knows, maybe we created a data structure and it's somewhere like after 10 other different fields, and it so happens that it sits in between the two cache lines. Like here your head should start blowing up because or exploding because it look like any move instruction. Everything what I program is no longer valid because it can be, you know, evicted halfway and you will see a turn right. So how do we prevent this from happening?
Isn't that why we use the lock, so that the other CPU can't try to get that address at the same time?
You can. You say, look, sure. In most cases, yes. The sanity is probably introduced by a lock, saying that, but what about the lock itself? Let's put it this way. What if the lock variable is split between the cache lines?
I think the hardware is supposed to guarantee caches that are sequentially consistent. So anytime that you read something from memory, it has to come back to the same order as if it was done on like a certain order. And then cache coherence. As you, if you're looking for a simple answer, you can just add an line and force the alignment.
Okay, I agree. So, but what part of the software stack does enforce alignment? Although everything what you said probably also is important, and I maybe not be even ready to explain it very, very carefully, but
The allocator,
the allocator.
you request sufficient alignment, then it'll be.
But what if it's a data structure and it's like it's aligned to the beginning of this cache line, but it so happened that your local variable is still split in between cache lines?
With compounder,
It's what?
It's kind of on the program.
Have you ever done it? Aligned padding, like okay. On microcontrollers. I mean, you're partially right, and again, it's such a deep argument that maybe you're right actually, but
Compiler also.
right. So this is an interesting observation. Compilers ensure a natural size alignments for those finite at 8 byte granularity, meaning that it will insert padding automatically here at the end of this data structure and will shift it to the next cache line. I mean, I didn't know for a while, so it took me a while to track it down. And I forgot exactly what triggered my exploration because I also was thinking, okay, it just works and works and works. But then I understood that, okay, look, the reads and writes are not guaranteed to be atomic in these cases. And so compilers ensure alignment of those types to their natural boundaries, which means that if you like a byte, of course, you still like within the cache line. If you are 2 bytes, then you will be aligned to make sure that you don't like cross the boundary of a byte. And I don't know, maybe you're right, and on some microcontroller architectures, the compilers do not ensure this alignment. Maybe that's true. And then you have to like be careful.
To be fair, I have to do stuff without optimizations.
Yeah, that probably can be also true. And you can override compilers, and that alignment, probably you say something like packed, right? Because for example, if you receive network packet and it's like your layout of the data structure has to match the layout of whatever the TCP stack sends you, like actual physical device, then you say like override that and just like, let's do it manually. But you still have to be careful.
How do atomic operations interact with this? Are they sufficient to avoid the problem? Like a sequentially consistent, right, as was mentioned.
We should call VJ or something. Okay, let me answer, but I shouldn't be telling what next. So, and the second thing, so first of all, like what is important that like data structures have this natural alignment within, and then the allocators also align to the, because if allocator breaks this convention, then you can be off by 1 byte, right? It doesn't help you if the compiler aligns. So your allocator also has to align, I would assume, to what? It's a good question. To what? But there must be done some alignment. Agree? Okay, just wanted to make sure that we understand this. Okay, so now what's the memory consistency, right? And again, like, not ready to talk about it, but on Intel, it's a total store order, which means that the system observes writes in the same order. And I think it's also in the order in which, like, it will not reorder writes, like write 1 and 2 will not be, this is called sequential consistency, right? It will not reorder W2 in front of W1, although some other architectures might, if I understand correctly, and then you have to put a barrier. But I mean, I don't want to, I mean, I'm not ready, so don't understand it. And the way it works is that when you try to write a cache line, the hardware or cache coherence implements something what is called concurrent readers, exclusive writers, right? So it means that this cache line, which contains this, the whole thing, can be in readable state on multiple CPUs, right? In a shared state. Like the coherence protocol will track the state of the cache line. The moment we try to write into it, it says, okay, I will first invalidate all other readable copies, meaning that this cache line stops existing. It goes to the invalid state on each other CPU, and on this one, it's received in the exclusive state, which allows the write. So physically, it's just like you send a bunch of messages to all the cores on all modern CPUs, and they say, look, yeah, I did have this cache line, and I invalidate it, and I confirm it, and after you receive all the confirmations, you say you're an exclusive. Maybe this guy immediately tries to read it again, right? And then since it's used the cache line in the invalid state, it says, okay, look, can I get a shared copy of this cache line? But the memory controller of this core says, okay, hold on a second. I will just finish my write, turn it into exclusive, maybe do a write back to memory because this cache line was modified and they like to write them back to memory, although it's not always true. And then it's again like either transported, like converted to shared state, and then all of them have the cache line in a shared state again. But this one will have to refetch this cache line as well, right? And so the cache lines are kind of bounced all the time between you, right? But the unit of this bounce is a cache line. So if you do a write in a cache line, it's always atomic, so it will not be torn, right? If you want to write something what's like crosses the boundary of a cache line, you don't have this guarantee, right? And at this point, you say, look, I will definitely have to acquire a lock, which will be, for example, sitting at the beginning of the cache line, and other people who try to write this, they'll synchronize on this lock and will make sure that this cache line will not go away, right? That's how roughly we can ensure tonicity of those lines, right? That makes sense? Everyone who was, it's kind of important because it's very easy to make a mistake. There are people, maybe in this class, or people who I met who work on those problems, and you'll be surprised how often we get those things wrong, even the compilers, because you need to like imagine some weird microcontroller which has a slightly different guarantee about whatever, and then it immediately falls apart. So it's not trivial. Okay, but let's get back to this thing. If it's already aligned at a natural boundary, so it's cache line atomic, right? We said, okay, sure. If we want to override it with a new value, like of this 80 timer, we can just do a write and move into it, right? Makes sense? Does everyone agree? It's also important to understand that this is possible, right? What can go wrong with this write?
If you just do a regular move, would it not evict the other threads, the other CPU's cache lines for it, so they'd observe an old value?
They can for sure, but again, so it's if another CPU like just about to serve as the timer interrupt and reaches this line and tries to read the handler, it can either read the old value which is totally fine, right? It's a valid behavior. Or if the write wins the game, it picks this cache line from this other CPU, and by the time we refetch, the new value is placed into this cache line. It's also a fine new behavior, like it's a new state of the system, so it's okay that we're going through this path, right? Agree with this? Sure. So that seems to be okay.
A move, so validate.
I don't know.
Yeah, I guess.
Hold on. This behavior seems to be fine, right? What if, like, erasy behavior? Erasy behavior is when two CPUs at the same time try to override this handler with AV timer and AV timer 2, for example. And the expected behavior is that one of those wins the game and either change them as AV timer involves AV timer 2, and then AV timer 2 involves the timer, or vice versa. It's kind of like inserting into the list, right? Agree with this? So this is a race, right? So it's very similar to a linked list. And if we just simply use a move, we might lose, there is a probability that we'll lose one of those handlers, right? Agree? How to fix this? Do we understand the problem? Although, like, at the level of cache lines, nothing is stored, just like a more logical, high level bug in which we would have a race and we might lose the fact that we installed another handler to this list, right? So how do we do this?
Compare and swap, maybe?
Yeah, so like again, like a traditional simple technique is really use a lock, right? Lock is again guaranteed the write into the lock variable, which like is guaranteed to be atomic because it's aligned to the natural size. Like typically you will have to use an atomic primitive inside because you will both writing and checking for the value. But essentially under the lock, one of them acquires the lock and then modifies everything. It's kind of like inserting into the list and guarantees that the second one cannot even touch this variable until the lock is released. When the lock is released, the second goes in and like sees the new state of the system and adds everything, right? Talia has an optimization. He says, okay, sure, right? I know that there are like atomic compare and swap primitives, and really there is a way to write this code without a lock. Don't want to go into the details. If people know what this compare and swap is, they understand what it is, but doesn't, or like it's what is the other primitive exchange, atomic exchange primitive is also can be used, right? This makes sense, right? So this is atomic. It's just like answering Manvik's question. Are you still following? Okay, but we got the atomicity. Like what's important is that types are naturally aligned. Allocators implement alignment, and by the way, if it's in the global section, I don't know how the allocation in the global section works. Maybe you have to. Hopefully, it's aligned as well. So someone has to answer those questions. And if you want to stack those handlers on one on top of another, you will. The simplest method is to acquire a lock, right? Agree?
Okay, so to go back to the beginning where we were talking about what does all need to be on each CPU core, the reason that I understand that we were talking about this was this in the case of each core having different interrupt handlers. Is that correct? And like we're talking about when these different cores write to their IDT and like how to make that. Is that true?
Almost. So Manvik asked a question about typically in our system, in our kernel, we will write IDT once at the CPU, bootstrap CPU, and we'll never touch it again. In a real kernel like Linux, which allows like dynamic overloading of interrupt handlers, supposedly, just for the sake of introducing those antivirus. I don't really know why would they do that. I'm not an expert, but it's possible and they do this. Then you need to some synchronization primitive to make sure that like to enforce the atomicity of writes, right? Of installing a new handler. Right. However, You follow it, right?
Yes.
However, unfortunately or fortunately, it's not how they do that. They used to do it this way. But then Linux doesn't boot on some meaningfully sized number of CPUs. Why is that? Because acquiring this lock and releasing this lock is so expensive that this machine doesn't make progress. That's probably a subject for a different lecture. And so if people are familiar with those words, what Linux, but like the reason I started answering the question, because I wanted to make sure that we understand the alignment issues, right? Because at least we should be familiar with the fact that this is what can happen, and like at least we need to reason about it. Linux uses a newer synchronization primitive, which is called read copy update. And I forgot if we covered it when we were talking about it. x86, I can come back later, spend a lecture on this primitive. This primitive allows you not to acquire a lock in case of a read, meaning that you just normally access the variable. And only when someone does a write, writers will synchronize between each other. The main observation for the RCU is that reads are extremely frequent, because every time you have a timer interrupt, you will have to acquire a lock that is fetch a handler and execute it, right? But wow, how often do you update the handler? Like maybe twice a day when you install a new antivirus, and when you reboot, maybe even like twice a month, right? So, and this is a primitive which allows you not to acquire a lock on reading and only on writing. That's a powerful primitive. So there is more and more, like essentially the Linux kernel almost got rewritten. I mean, they first used something what is called reader-writer log, and then they moved to RCU. And RCU is like, it's a very powerful primitive, which allows them to ensure consistency of those accesses in many different cases. So worth knowing, again, especially again, compiler people and everything. Okay, so let's leave it there and just believe me for a second that RCU does work. And if you don't, like in our case, we're not going to build RCU. For us case, we'll have to use a mutex on this if we want to quickly access the address of the handler, release it immediately, and then just proceed with the execution of the handler. But it will slow you down because acquiring a mutex, it triggers a write into the lock variable, this transition, and everyone else essentially, whoever on the other core will loses the cache line in a shared state and has to refetch it every time. And that slows everyone down. Enough so the system starts, like we'll see a significant performance overhead. Okay, so Manavik.
Just thinking of now, so we have one global identity, and if anything wants to say define some custom handler for write to it, we have a thread global identity for just that particular thread.
Which one? Like which
So if any thread wants to like kind of update your identity, we say that okay, we'll create a new identity which is like local to that particular thread. But all the other threads still use the global identity. Can you do something like that?
Yeah, you can. Like again, it's an exotic case, and I don't have a good answer. But imagine you have like imagine you have a infrastructure which maybe completely changes interrupt delivery for this specific thread or process of execution, right? Maybe this IDT gets overwritten and the interrupts are routed to the user level memory or something like that. Then in the context switch, you will have to implement support that IDTR register of this specific CPU core will be loaded with this other IDT. Again, never seen it in practice. Like I almost seen it, or maybe seen it, but I cannot even recall this case.
Is it ever useful or safe to have a handler be in user space code?
Yeah, so this is what for sure. And it still seems to be like a not super elegantly solved issue, but totally can be like, imagine you writing a kernel which supports some, I don't know, high frequency trading applications or something, and you willing to compromise everything else, like even like maybe security guarantees for whatever reason. But still, you say, look, I'm not going to implement my core in a kernel. There's lots of like floating points, lots of some other optimizations which kernel doesn't support very well. So I really want to write user level code, but I hire someone talented who can, like, really code the interrupt processing pause in such a manner that if my thread, which does this high frequency trading, is running, and it made it up, so I don't know the answer. I don't know if they do anything like this. Then this immediately switches, like the interrupts are delivered to your thread. And maybe it costs you like by half a second somehow. Not half a second, I don't know, like 300 cycles, let's put it this way. But it's possible. And people are talking about it, but I never seen a good solution. And I think we talked with one of you about the possibility of building something like this. Like, for example, what happens if the thread is running, but some other interrupt comes in, like a disk interrupt, and this thread is not interested in processing the disk interrupts. They have to it has to go back to the kernel, and you can trust the thread to correctly call some plumbing in the kernel to say, look, there was a disk interrupt and stuff like that. But so it gets a little more non-trivial, but it's doable. Okay, any other questions? Actually, okay, but so sure, let me unroll this wonderful discussion about alignment, timer interrupts, what we really wanted and cache lines. And again, I'm not even ready to talk about sequential consistency or other consistency models, which is embarrassing, but yeah, sure, I just don't remember how they work. But TSO is powerful enough that if you just think in terms of, okay, I got it. So cache line is always atomic, it bounces between the cores, all the writes go in some natural order and observed by the system in the same order. So if I have write one, write two here, then I can either see write one, write two, but never will see write two if I don't write one. And if someone has a write three here, so it's quite possible that it will be in between these two writes. So it simplifies your logical model a lot. Although it's not the case on all the CPUs which you see in existence. But sure, okay, wait, wanted to get back to this. So we have one global IDT, right? Forget about those overloading handlers, just one global IDT. Stacks are per thread, GDTs are per CPU, right? TSS is also per CPU, and with the expectation that every time we context switch, we overload the stack, because it can happen that we'll get preempted later and our state will be saved on this stack. And so our thread data structure will look something like, there will be a process data structure with a pointer to a list of threads, and inside the thread we will have a pointer to the kernel stack, right? And if there will be a different thread of the same address space, then it will have a pointer to a different kernel thread, right? Make sense? It's important to kind of have it in your head, because like anytime, roughly speaking, someone asks you a question without having this model, you cannot reliably answer the question, right? And the process itself will have a pointer to the page table. And this thing, when we context switch, we'll load it into the CR3, right? Make sense? All the threads will share CR3 of the same address space. Makes sense, right? Because threads do share the address space of a process. That makes sense? Okay, so now for thread, we agreed on that. Okay, now we wanna, back to my question, how do we initialize this system? What kind of initialization code we have to run on the application processors to make sure that this thing is running? On each processor, on each application processor.
Seems kind of logical to me to follow the same sequence of steps to the degree possible as on the bootstrap. So like, I would first think you would need to write to the page table register. Then all of those like per core data structures, I would start filling those in with like new instances. And yeah, that's kind of how I would start it.
Correct, but we don't need, like, what I wanted to emphasize is that we don't need to initialize the like interrupt descriptor table second time. We just simply write on each CPU, we write IDTR register to point to this interrupt descriptor table because it's global, right? We will have per CPU GDP, so we'll have to allocate space for it and just make sure that we have it. We have a per CPU TSS, again, allocate state. It seems to me that it's logical for simplicity, or like, I don't know, like, it probably can be constructed differently, but it makes sense to have a notion of a idle process.
Like on each CPU.
I think it can be one global idle process, and then on each CPU we can have an idle thread running.
And when you say idle, are you saying like it's kind of the kernel's logic?
It means that idle will probably, the goal is to return to this scheduling loop. Okay, let's get to it, and we'll wait for some timer interrupt to see if any other threads are ready to run. So actually, the question is like how to structure it more conveniently in terms of code. So, but roughly speaking, all these idle threads, they try to context switch, they try to schedule some other thread, and if they don't find any, because maybe everything is blocked waiting on IO, or maybe we have more cores and threads in the system, it says, okay, there is no runnable threads, and then we just simply do the alt instruction, save power, just enter some low power state on this CPU, and stick there, not doing anything. When the timer interrupt arrives, it brings CPU back to the like real executable state. We continue next instruction from the HLT, try to schedule the thread again. If we find one, we switch to that thread. The thread is running until the next timer interrupt. When the timer interrupt comes back, we go back, switch, we get preempted, and we search for the solution and say, look, guys, is there anything we can switch to it? Are there any threads which want to run on this CPU? And if we find none, we don't have to context switch, we can just continue running the thread. And if that thread is non-runnable because it's blocked on IO, we switch back to idle, right? So idle plays this role of a thread which is always there. It doesn't really have to be a thread. We can probably structure it differently with some like corner case pieces of the code, but just like enter this loop again. The only thing we care about is that it has the kernel address space, this one, and it has each of this, it has a separate stack of execution on each core. So we can actually like context switch and maybe even delete the thread which we actually were running a second ago, right? So this is how we structure the system. That makes sense? Or it's okay. It's hard towards the end. Okay, so what we do here, so how to implement it, how to write it down in Rust or in C, or any other questions first, maybe, if we have questions. So, okay, wait, hold on. Did you get the goal? The goal is that on each of these application CPUs, we will enter some kind of loop, which I keep calling idle thread, which will try to schedule other threads from the scheduler, from this queue of runnable threads, this queue of processes. You might maintain a queue of runnable threads from all processes in the system, and we'll try to like switch to those threads and run them.
So I feel like I don't understand the very first step we do, which is how do we set up some code to run on a CPU other than the first CPU?
Yeah, so I didn't explain it. Let me just, it's very easy actually. But that's a good question. So, okay, sure, let's switch to this. So the protocol to wake up those application processors is to send them like, it's a well-defined interprocessor interrupt. So it goes through the advanced programmable interrupt controller. I'll show you the code. It's nothing super interesting. It takes only one argument. It takes an argument which is an entry point thing. And which means that you send it from the bootstrap CPU towards the end of the initialization. You say, like, I initialized enough. I will run a loop waking up all application processors. You send an interrupt with an entry point to this processor. This entry point starts executing. At this point, how do we, it's more almost like a main function, but if we call this, maybe we can call it AP main. If we want to write this function in Rust, we obviously need a stack to start even executing, right? Because maybe it pushes something right away. So as I mentioned, it's an interrupt essentially, although it's somehow hidden. We don't have to set up anything in the interrupt descriptor table. It's just like magically handled by the hardware itself. Starts running from the entry point, which we'll provide. But the question is like, where do we take the stack from?
It's like the memory for your new main function.
You can just build a memory allocator, hopefully in Rust, not in assembly, right? So if you want to invoke a memory allocator, you also need a stack. No, it's like, that's a right logical line of reasoning. I mean, a second ago, as I was typing those letters here, I was thinking, okay, can we just allocate memory? Almost, because we need a stack. So we cannot. So it's kind of a chicken and egg problem. So how can we handle this? People who did x86 class. Who remembers?
But
Well, maybe halfway, but okay, hold on. Like it's not as hard. It's almost like you think that I'm playing some kind of a game. The game is very interesting. So it's not as interesting, honestly. It's very mechanical. So remember how we booted on the very first bootstrap CPU. We started from assembly and we somehow like figured out the stack, and we loaded into the stack pointer RSP, right, and start running. So we got the first stack from like our global section, right? So global from the data section in the program, right? Which maybe we used assembly to allocate the variable, maybe we used Rust to say that it's just giant array, right? So intuitively you say, look, okay, sure, if I want to run Rust code, I need to implement some kind of a small assembly trampoline, which sets up the stack and then starts running this AP, and then it just calls AP main. Right? So this assembly trampoline, we can write by hand, making sure that, okay, it doesn't use stack at all, right? And the question is like how to pass. We can, for example, before sending this interrupt on this core, we have everything. We can allocate a stack, like go to our memory allocator and say, look, like, give me like whatever amount of memory, like 2 megabytes, for example, because 4K seems to be a little smaller, and have a page of memory allocated, like if it's virtual addresses, like for example, this is like stack for CPU1, for example. Now our only goal is to pass the pointer to this stack to the other core. So how can we do this? Alia?
What if we had the assembly be kind of like a template, and then we fill in the hole for the address where the stack is? So like, there's a move, or we move the stack address to RSP, and then we put the source, we write into the source of the code.
Okay, let me explain what Tyler is telling us. It's a compiler person talking. They say, look, guys, I don't care about variables. Everything will be in the code. There will be no variables. And Natalia says, okay, I will do a move instruction, and there will be some address. And I say, I figure out this address, and I will just write it kind of like dynamic linking and loading into this on top of this move instruction, and everything will fly, right? And here will be ours, right? Agree with this? Doable. I don't know, like your teammates might be offended with this approach. If you're like, you know, well-respected member of the team, what's wrong with this approach? What's not ideal? It's totally working.
Well,
Or anyone, like, will you accept this patch to your code base?
seems great.
Seems like Talia.
Yeah, I guess.
My first concern is something that I think doesn't matter. It's typically, say, stack length.
Wait, hold on. What maybe, wait, hold on. Like logically, it's kind of like an involved change. So you either have to like implement some, if you want to make this general and you don't know, like this trampoline is not linked to a specific address, it can be anywhere. You can like, and maybe compiler changes once in a while, the move layout changes, maybe fix a slightly different instruction or instruction encoding if it's an assembly. So you really need like a relocation table to understand like where really this address is to patch it, right? But also like anyone in a sane mind, oh yeah, hold on. Guys, like listen for a second. Says, okay, wait, hold on. Why do I need to patch this address? Let this address just be pointer to some memory location, right? Yeah, like here. And this memory location is always the same. It's a global part of the global section. We just like write the pointer to this stack into this location, like one level or 3 direction. We don't need to patch anything. This is just an assignment.
But then how do you start the next thread?
Yeah, you wait for this one to finish. Yeah, no parallelism. You give up for parallelism in bootstrapping CPUs, right? Or at least in this step, maybe here you release the log saying, okay, I read this value, start another thread, right? Makes sense? So a little easier, and it like uses just store programming primitives. You just assign the variable of this new stack, right? That's a little easier. Agree? Like, okay. Alex?
Oh, no, I'm just trying to follow.
No, like it's just a variable memory, global variable in a data section. When you allocate a new stack, you just write a pointer to this variable, and this will just compile it to read this variable. So it's not, it's just like whatever. It just, you declare it as a CX turn global, whatever. Assembler sees this, Rust sees this. You can just simply assign, right? And the synchronization protocol is you have to wait for this thread to start, right? And to read this variable, after that, you can assign it again. Make sense? Right? Okay, so this is pretty much how this can be done. So you need to pass the stack, then call the AP main. AP main goes, initializes, okay, let me ask a question. So where do we get those GPT, TSS, and other things?
AP main have to like ask that.
Yeah, so that's one way to just like inside AP main, keep allocating memory. That's totally fine, honestly.
The bootstrap process could allocate it and put it in the same global separate memory.
That's also another like essentially the logic here is and both of them work honestly, and I don't have a strong opinion. So like in the code you will see two different solutions. One is says that this DDT and TSS are per CPU data structures. That's convenient because it will be easier to find them later, because sometimes you have to like you have to keep track of where the TSS is, and you can either keep a track of a pointer or you can keep a track of where the TSS is as a per CPU data structure. Why do we need it? Because every time we like in a way, okay, so let me explain why it matters. In a way, those data structures like GDT and TSS are the kind of like global variables. So you will see a lot of spots in the code where you just say, okay, give me access to this TSS, but what you mean is not the TSS, which is another CPU, but it's really yours, right? And so it's kind of like a per CPU variable. Right? Remember, I talked about thread local. It's just a global, but it's per CPU. So it's global, a different value on each CPU, right? And you can always write around it. You say, look, I will have my maybe CPU variable, and then it will have a TSS, and only the CPU is global, and TSS is just a pointer with it. You can write the code like this, right? So, and there is no real strong pros and cons, as long as you have one entrance, one entry point into those per CPU data structures, which allow you to say, look, on my CPU, the TSS and such, on my CPU, the GDT and such, and that's only needed to make sure that you can update those pointers. Like, and typically, since we only will be swapping this pointer, right, on context switch, we never will change the TSS connection. We just initialize the GDT to TSS only once on inside AP main. We only will be accessing probably this field of the TSS data structure on every context switch, right? Makes sense? Okay, hold on. Like ask your questions. So you asked Talia how we initialize those, but I was asking a different question before, and I forgot which one I was asking.
Before my question, you were talking about the idle loop.
Yeah. Okay, so okay, sure. So we are almost there. So inside the AP main, right? So like AP main roughly becomes our idle thread, right? So we don't really explicitly create an idle thread. We just have to maybe stitch them somehow together. But the goal here is that at the end, very end of every AP main, we can say, look, I'm entering this infinite loop. And what I'm doing here is that I will try to schedule the next thread of execution. And if I have it, if this T is non-zero sum, so then I will switch to this T, saving, and this is the same switch function which you can say I will yield to T. And inside yield, you will do a switch which saves the context of the idle thread and switches to T, right? And next time the timer interrupt comes back, you don't have to switch back to idle. You really can just probably switch like from T1 to T2, but just make a scheduling decision, right? And switch to another thread. But at some point, when all the threads actually become non-runnable, you yield and there is nothing else. The scheduler says, okay, by the way, guys, if no other threads are running, I will instead of this T, I will return you a pointer to the idle thread. And idle thread will have this stack on which the state was saved, and essentially return from this switch, and will enter this scheduling group again, trying to like pick a different vector. Right, makes sense. And this is essentially how the kernel will be run. It's the same what x86 is doing. So they maybe choose slightly different naming for. They don't have a concept of an idle. They just have this. I forgot what they call it, main thread. But essentially, on each core, they run this loop of scheduling group, and just always like return to this loop group, picking the next thread to run. So let me. I think it's 15 minutes after the hour, so I should stop like some last minute questions. So my plan for today was actually, I mean, I didn't realize that it will take me so long, but my plan was to look into the implementation of this schedule function and figure out how this scheduling algorithm works, how we maintain this list of threads in such a manner that we can implement some meaningful scheduling policy. Although it's harder than it, and I don't know the answer honestly. Like, and then we'll see next time, but essentially they picking the thread which in a fair manner to make sure that the next thread has a fair fraction of CPU. But okay, but at least we got this execution model of the kernel. So we booted on each machine. We did initialization of the bootstrap CPU. We woke up other application CPUs. We understand the layout of those data structures on each core, on each logical processor. We understand how initialization works. We understand how the boot ends with this scheduling loop, which we call the idle thread. So, and pretty much at this point, if you got all the pieces running, like your scheduler will pick the very first process which we created, and it will come with the thread. And from this, the system starts evolving. At some point, you switch to the thread will make a first system call, create more threads, starts booting like applications on this kernel, right? But essentially, at this point, roughly speaking, the kernel is complete. I mean, like, okay, sure. Like the only thing which we discuss is interprocessor communication mechanisms. We'll talk about them, but it's pretty much a usable system at this point. We only need to start building device drivers to build IPC. So, and discuss scheduling. Okay, this is where we are. Okay, sure. Let me stop here. I'll try to push the homework. The next homework, probably over the weekend, honestly. Get there. But sure. Okay, thank you guys.